Yeah, I wanted to build a function generator as a tool with a LM324 square wave, triangle wave, sine wave output, but it needs a dual power supply, plus minus 5 to 15 volt. I don't have that. I could of course go and buy stuff, but could we build it ourselves? And yes, let's just look at this page from All About Circuits about a virtual ground. They suggest a simple voltage divider with some capacitors. They talk about how you can achieve that, drawbacks. Then they suggest an OpAmp, drawbacks about that, some drawings missing, and just a single OpAmp with a voltage divider in front of it. And it has, of course, the drawback that it only can push-pull about 20 milliampere. They suggest other components to buy. Again, don't want to buy, want to build something. Single transistor suggestion based, again, on voltage divider. Push-pull configuration, that should be better on voltage dividers. About drawbacks with that is coming again. The temperature coefficient influencing the resistors differently than the transistor. So they put in a diode and end up with improving it with an OpAmp based on a voltage divider. So I will go for that. But this drawing has no resistor values. So what are we doing? Searched on, and on another page I found again, starting with different two batteries with the capacitors down to something like a voltage divider again, an OpAmp. Then they talk about drawbacks, unequal virtual ground splits, ways to fix the problem, and they can again suggest buy stuff. I don't want to do that, I want to build something. And we end up with this down here. Again, with a push-pull configuration, but no OpAmp. And they then suggest something more complicated. And again, with an OpAmp, you only have a push-pull of 20 milliampere. They suggest more buying the same component, actually. Yeah. So the most attractive was actually this one, but I want the OpAmp inside to make it more precise. So I created the circuit in KiCad based on the OpAmp and the push-pull configuration. Yeah, and when I started out, I forgot the K here, so it was 220 ohms only, which made it use 29 milliampere through these two. That's a little bit much, so you could use from 100k to 220k ohm on this side. A power supply here of, for this now, 18 volt, and the circuit is finally only this part. On the right side I have measuring for this is the virtual ground in the middle, and measuring the positive voltage and measuring the negative voltage. And this over here is just a test circuit for seeing how the top side reacts, expecting the bottom side reacts equally. Yeah, this is how the circuit looks. And we could go up to this sign up here, push it, and we can run a simulation. And we can see down here that we have some simulation points, no errors. And we have to note this is an SPICE simulation of in KiCad. And this is not any special OpAmp. This is a simulation OpAmp. So ideal stuff, blah blah blah. The transistors is the same actually for this simulation, so they are off in values and they can react a little bit strange. let's see the simulation. Next to running simulation, we have to add some signals. I'm interested in the input side of Q1, so the collector, next to the two voltage meters here. R7, why doesn't it react? R7 just to see how much ampere runs through, milliampere. R3 just to see how much milliampere runs through here, and a check on R1. So I will select R1, R3, R7, Q1 collector, and which could end up being the same as ampere running through Q3. But yeah, let's see the simulation. The ampere of Q1 collector. We go down, hold down control button, select the two voltmeters, and then we want the ampere of R1, R3, and R7, and let's see what that shows. Yeah, so we have, we will add one more. Where is the collector voltage of Q1? I wanted that to here. This one, I'll add that. Run simulation. And we can see on the left side is the voltage for those with a V in front. And on the right side, we have the ampere for those with an I in front. And we can see we have 18 volt on Q1 collector side. That's the power supply, single rail. And we can see we are on 9 volt on the positive side and minus 9 volt on the negative side. And when we go into the ampere, yeah, we have the voltage here from Q1 collector. Yeah, on the ampere side, we can see there runs through Q1 collector between something like 12 milliampere to 86 milliampere, and that's the simulation based on the consumption on the right side. And then we have the blue, the green, and something else. Yeah, that's R7 is representing the collector current, actually, so we can leave out that signal. Let's zoom in on the consumption down here. And R7 representing the output, the current running through the output. Again, somewhere down here we have, yeah, 12 milliampere. Up here we have almost 90 milliampere, so 87 milliampere output. Looks good, no strange stuff. R3, which is up here. We have the green one, and it's quite down 2 milliampere more or less. And of course R1 is using almost none. That is the input for the OpAmp, the voltage divider for the OpAmp. In the final circuit I have matched those two, so they are as close as possible. And I have tried to match R3 and R4, also match R5 to R6, and as far as possible R7 to R8, those 10 ohms. And everything looks nice, tidy, cleaned. And we can at least draw 85 milliampere, and potentially even more. If we use original 3904 up here and 3906 down here. yeah, so this is the circuit. You can build yourself, and I've already done it and can show you how it looks and take a measurement on the output. Before we do that, we can just test it with 12 volt, just for the fun in the simulation. 12 volt on the top, 6 volt and minus 6 volt, and again the ampere there, yeah, there, 86 milliampere, not showing any problems. Yeah, and let's check the circuit without load. I'll show you. We have the build of the circuit here, just on basic general PCB board, and I've checked it once, and it is connected to the 12.26 volt, I think. We can measure it now, and I'm recording on my mobile phone. Sorry. And let's just check the input voltage. We have 12.25, 12.26 as the input. This OpAmp is 741, and I have 2N3904, 2N3906, a PNP, NPN, the 2 times 220K here. The top first pin is here on the OpAmp. The feedback is coming from these two, which is actually also the output, the middle of these one. This will be the positive side of the half and the negative side of the half. So minus around 6 volt, 0, plus around 6 volt expected. Yeah, and on the right side of the output of the OpAmp, it goes to controlling the base is over here connected to this point, and the base of the PNP connected to this point, to these two. Yeah, and these are the 10 ohms, these two. 4.7 kilo, 4.7 kilo, 100 ohm. Yeah, let's start some measurements. As we've already seen, the input voltage 12.26, and the output is going from here to these two are the outputs. This is of course measuring positive here. So if I have ground up here and positive here, we can of course see the minus 6.13, slightly off the half, but very slightly, only less than a hundredth of a volt. And we change around, measure from the center point that is there up to the positive rail, and it shows 6.12 volt. So it's exactly in the middle, a hundredth off from the middle, and we could of course use a bigger range depending on the OpAmp and transistors we have. They can take quite more, the transistors, the OpAmp too. Yeah, so this is working and quite precise. Thanks for watching.